Okay, well, we'll go ahead and get started. Today, I'll be presenting on, as you can see, creating a digital surface model, DSM, using LAS tools and ArcGIS Pro. Now, a lot of the techniques I'll be talking about today, or the tools I'll be talking about today with LAS tools, you could use very similar tools to help create a digital terrain model, DTM, or a bare earth model. I will be focusing on the DSM, highest hit type of model, simply because that's the project that we're focusing on now here at the GIS Center. And what we're doing, of course, is we are using Lidar to derive some kind of important layers for the state of Idaho. We have already assembled a digital terrain model in a image service. Digital terrain model, remember, is another word for a bare earth model, essentially or sort of a DEM. And these are stored in the GIS Center and on our servers. These are stored in TIFF file format. And that layer is available, as I already noted, available as an image service. So you can skip downloading anything and just stream in that image service. And you can do quite a bit of analysis with that online or streaming service without having to do any downloading whatsoever. But what we're going to focus on today is this digital surface model, or DSM. It's a raster image stored also in TIFF file format, providing elevation for natural and built geographic features. In other words, and this is literally a DSM that we generated for a part of Idaho, and you can see when we drape over the nape, we drape the nape imagery over the top of it, you can see the trees. You can see the rocks and all of good stuff like this. So it is quite a bit different than your bare earth digital terrain model. And of course, if we subtract the two, we then get a canopy height model from that. And with these data, once they're completed, you'll be able to do that if that's something of interest. Well, as I said, we're going to focus on DSM. Why should we create or even use a DSM? Number one, like I just showed you, data visualization. There is a lot of things that you can learn about a landscape by looking at it and doing that 3D rendering, as I did there in ArcGIS Pro. Really does help a person understand the landscape. As I already also alluded to, we can determine feature height or canopy height, the DSM minus the DTM, and that's useful for vegetation mapping and improved land cover models. The latter comes in really handy if you know that a certain shrub grows or tends to grow only to a certain height. You can use the canopy height model to differentiate one land cover type from another, even if they're both deciduous. One's a deciduous shrub, another's a deciduous tree. That height model can help you improve land cover layers or land cover maps. It also can be used for structure mapping. The height of a building is certainly going to be a pronounced difference in height above ground, so that can help you identify where structures exist, and the fact that those structures tend to be very linear in their shape can help differentiate those things from natural forested or vegetated areas. We also can use, and this is more along the lines of the things we do here, the research that we do here at the GIS Center, is to evaluate the effect of disasters, disaster events, disturbances. And most of the research that we do here related to disasters is focused on wildfires, but certainly looking at how that landscape has changed using a DSM or DSM minus the DTM can help us understand again how that landscape has changed because of a wildfire. And also, the next bullet right down there, to monitor post-disaster recovery. A forested ecosystem, perhaps 10 years or 15 years after the fire, should be showing some regrowth of those forests or of the trees themselves. And so again, using Lidar and this approach we just talked about here can help you monitor post-disaster or post-wildfire recovery. Okay, so creating a DSM, how do we do it? You know, in some cases, the Lidar project data, as delivered by the contractor or the vendor, will contain what's called highest hit. It's also sometimes called maximum surface height. Again, those are all going to be rasters, and normally we see those delivered in TIFF file format. Those may be identical to a DSM. Um, so it's not really absolutely synonymous words, HH versus DSM, because there may be some anomalously high hits in that highest hits layer if the LiDAR point cloud was not filtered or if it's not filtered. Sometimes what we see, and it's actually fairly common, that the highest hit model will include birds. Something up there in the sky that laser pulse that's stored in the underlying LAZ or LAS file strikes a bird, that then does become the highest hit. However, we do not want to count that. We do not want to see that when we're creating a digital surface model or, top of canopy type of thing. So we need to filter out that data. That's where the DSM workflow using LAS tools comes in. We use LAS tools. We've been using it for years. That's created by a company called Rapid Lasso. And it's free. It's free for use for small project areas. The stuff we do across the whole state of Idaho is not considered a small project area, so we use the licensed version, which, by the way, is only a few $100s per year to maintain and to have that full license. And then, of course, there's no restriction to the number of points that you're processing, to the size of the data that you're processing, and all that good stuff. So real good, real nice software here from Rapid Lasso. The nice thing about LAS tools, some of the advantages of LAS tools is, number one, we can process LAZ files directly. We do not need to convert them to LAS file format first. Now, we, just like the USGS, on our servers, we store all of the LiDAR point cloud data in the compressed or zipped, if you want to call it that, LAZ file format. The difference in an LAZ file versus LAS in size is about threefold. The LAZ file will be about 3 times smaller, or the LAS will be 3 times larger than the LAZ. Do you lose any data? No, not at all. It's just that it's compressed, and that's why it's so much smaller. Unfortunately, ArcGIS Pro cannot read LAZ files directly for its actual processing, so you would have to take the LAZ files either from us or from the USGS. It's a real standard format, and you'd have to run convert LAS first before inside of ArcGIS Pro if you want to take that route. So we're using the LAZ files directly. That's a huge advantage, and those smaller files also process faster. Simply because they're smaller, they'll process faster in LAS tools compared to other Windows desktop GIS software. Another big advantage of LAS tools is that it can run on a Linux computer. When we purchase the licensed version of LAS tools, we receive both the Windows application as well as the Linux application, and we're welcome to use it on both systems, one system, whatever we want. So what we've done is we have worked with our supercomputing administrators here at Idaho State University and have installed LAS tools on the C3+3 high performance supercomputer just up the road, about 40 minutes away. By the way, if you don't know, C3+3 is a collaboration between the Idaho National Laboratory and the universities across the state of Idaho, obviously including Idaho State University. So all the same LAS tools that I run on my desktop also exist out there on the supercomputer, and we leverage that quite a bit. Well, the other side, I guess, there's always a dark side to it, or a disadvantage, is LAS tools is command line utility. Now, some folks get scared when they see something like this. They like to see buttons to click on, those sorts of things. But it's really not difficult at all to use command line types of utilities. And there's lots of those sort of capabilities out there. Let's take a look at what this really does. Number one, we're going to download the LAZ file, let's say, for our area of interest. That you would do no matter where you're going to process it, whether it's ArcGIS Pro, LAS Tools, QGIS, whatever it happens to be. Then what we do, of course, normally it'll be zipped up. Very commonly, it'll be zipped up. We'll extract that file wherever we need it on our hard drive. And then using the command prompt, or if you prefer, the Windows PowerShell, either one works perfectly fine. We're then going to navigate into the directory or folder containing those LAZ files that we just downloaded. So I just do a change directory, space, start right where I am, which happens to be on the G drive, Lidar folder, and I'm going to go deeper, right? So I'm going to go into the North Central 2025. That's one of the projects we just finished up processing here. Brand new project for the state of Idaho, fills in a lot of empty spaces in northern Idaho. And then there's a subfolder LAZ. So we're just going to do this change directory. So we do that, and let me just kind of break that down for you. The next step where we actually run LAS tools, that first command that we give it is called the LAS height tool. And we're going to use the faster, newer version, which is a 64-bit version. So it's LAS height 64. And we tell it that we are going to have an input of all of the LAZ files, star everything, .laz, that it finds in my current directory, which, as you saw on the previous slide, was that LAZ folder. The output of this processing is going to be stored also in LAZ file format. If for whatever reason we wanted the output written in LAS, because maybe we want to do some additional processing inside of ArcGIS Pro, well, that's fine. We would do the dash output LAS instead. Then we're going to have another parameter in this command. Okay, so this is the command, LAS height 64. All of these are parameters, and I purposely put them into different colors so you can differentiate one parameter, input, output format, output directory. We're going to write this as a subfolder called the denoise folder, because that's what we're doing. We're using LAS height to denoise or filter the LAZ files, to get rid of those birds and that kind of stuff that otherwise kind of messes up our DSM. By the way, this folder has to exist before you execute this command. It will not make the folder for you. So lots of software is like that. Most software is like that. Just make sure you create that output folder as necessary. Then we have another two parameters. We're telling it that we want to drop any point, LAZ point, this is a point return, above 50, so that's the absolute height, and may as well also drop anything below -3, anything below ground. We want to get rid of that because you have to understand that very commonly that DSM, if the DSM surface is supposed to be equal to the DTM, the bare ground, which is very common, um, that we also want to get rid of anomalously low returns from that Lidar point cloud as well. So that's what this thing does. Now that last parameter here is just kind of a number one, it's a convenience. It's telling the last tools to be quiet. It doesn't have to show me everything that it's doing. Finished processing this file. Then it finishes. And if you've got thousands and thousands of files, I don't need to see everything that it's finishing. Whenever we tell it to be quiet, because there's not that output to the screen, it actually does run faster. So some of you have done some other command line processing. This is where we tell it not to be verbose. That's oftentimes a command that's used. So we're telling it to be quiet, and I like to do that simply because it runs faster. Then, once we finish the denoise process, we're going to run a second step, also in last tools, and this is called last to DEM 64. Again, a 64-bit version. It says DEM, and it also says last. We're processing with LAZs. That's fine. It's not really creating a DEM. It doesn't matter. Really what it's doing is it's going to create a raster version of all these LiDAR point cloud data that happen to be stored in a LAS or LAZ file format. So don't get hung up on this. It doesn't mean that it's actually creating a bare earth model. It's creating a raster for us. Again, that's the command. And here's our first parameter. The input, go into the denoise folder where we just wrote all of these LAZ files. The output file format is TIFF. That's what we want. We want first only returns. That's essentially going to be our highest hit. But because we denoised it, it should all be very real returns. And then we put in a couple of these things here, thin with grid 0.5, run an extra pass. And I'll talk about what those are here in just a little bit. And then step one. This one's really important. So thin width, this provides real simple thinning. And so when you're setting this, this is a recommended value when we are running what they call step of 1. Step of 1 means that the output cell size is a value of 1 unit. And because the spatial reference system of this LAZ or LAS file is in meters, well, that simply means that the output raster TIFF file is going to be, or is going to have 1 meter pixels. So normally we would set our thin width grid to half of that, okay? Or really it's a quarter, right? Because we can fit 4 half-meter pixels into one 1-meter pixel. So there's no reason to have tremendous number of returns inside that. So it's just telling it to thin with this, and that's the most that we would do. Just makes it run just a little bit faster. Person could omit this and may not really see much appreciable difference. There is also another command called blast to DEM, and it also could be used instead of LAS to DEM. I prefer the LAS to DEM simply because it is a little bit faster, but the output is very, 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 very similar. Almost no difference between the two. Blast, its advantage is if you have very high density LiDAR, I would then use blast to DEM because it can handle billions, literally billions. That's why they use BLAS. Um, it can handle billions of point returns. So that's probably also why it's a little bit slower, is that it's looking for so much data in its input as it's running. But same results, extremely similar results, and I say faster is better. Now I can run all that, and we've done a lot of processing here on our own Windows workstations, but we can also, as I alluded to earlier, we can run these on a supercomputer. The Linux syntax is so similar to Windows command line, but there are just a few differences. But we use the exact same tools. The exact same LAS tools are used. I use LAS height 64, LAS to DEM 64, exactly the same way. Why should we use a supercomputer? Well, remember, faster is better. For example, and this is real, I tested this. Last height on a GIS training, and here, one of our Windows workstation required, get a load of this, 12.77 hours, 766 minutes to process 661 LAZ tiles. This is real. That's 661 tiles for that North Central Idaho 2025 project collection that we literally just finished up working on last week or something like that. Everything's been pushed to the servers, ready for you to download as you need it. This particular workstation has a nice big graphics card on it, plenty of RAM, good amount of RAM, and a very new, relatively, well, quite current processor on that. 766 minutes. I said, that seems awful long. So I ran it again on another workstation, and it took even longer. 18.75 hours, 1,125 minutes. Now, I will note that this workstation in this particular test was actually running some other tasks at the same time. So it's 100% of its CPU was not given to LAS tools. In the previous example, that machine was doing nothing else. It was otherwise idle. So that's probably a better, that is a good gauge. 766 minutes to process 661 LAZ tiles. On the supercomputer, those same 661 tiles were processed, not a typo, 6 minutes. So, there we go. Started the process at 9:39 on that day for this step, ended it 6 minutes later. Insanely fast and wonderful results. No difference in the results whatsoever. Why is this so much faster? A little bit of an aside. It's because it uses what's called parallelized processing. Those 661 LAZ tiles are a job that we call perfectly parallel or parallelizable because there's no interaction between those individual tiles or files. So what happens on a supercomputer is those 661 tiles are seen as 661 jobs. And because those supercomputers have lots of cores on them, as in thousands of cores, each of these 661 jobs is simply parsed out to a core on the supercomputer. And in no time at all, the core is finished with its tile and the whole job is done because all the cores are done. In contrast, Windows operating system processes everything sequentially. It just starts chugging away. I don't care how many cores you have. It starts chugging away, 661 tiles. It does the first tile. It will not do anything with tile number 2 until tile number 1 is done. And so sequential processing, simply by absolute nature of how Windows is set up, is always going to be slower than something that can parallelize, even if you supposedly turn on the little check marks to run parallel processing. It does not work the same simply because Windows doesn't allow it. There are some optional steps. Now, if we want a single DSM layer, which we do want, what I'm going to do then is I'm going to download those TIFF files from the supercomputer. Doesn't take hardly any time at all because the TIFFs are really small in comparison to the LAZ files. And then I'm going to go into ArcGIS Pro. TIFF files work beautiful in ArcGIS Pro. I'm going to create a mosaic data set. In this case, then, it will contain those 661 TIFF files, which is the output of this, as you might recall. And then I'm going to use the copy raster, or in some cases, you might prefer to use the export raster. Take all that output from the mosaic data set, and it will save it as a single TIFF file. Pretty easy to do. And it's going to chug away at it. It may take, an hour or so to a couple hours maybe for a pro to get this stuff finished for us. But that then is essentially our final product for a DSM. We do some testing of it against bare earth models and so on. But that is that process that we're using to produce digital surface models for every project, Lidar project in the state of Idaho. And before the end of the summer, I'm sure we will have that finished and ready for use. There's a lot of those DSM files already out there on our server. Once we get the whole state done or all the state's files done, we will turn that DSM also into an image service that you can use just by streaming that data in. So let me open the floor for any questions that you have.